Hi everyone. We're getting close to wrapping up chapter 7, and there's actually a number of things left, but in terms of the descriptive material, we're getting close to wrapping that up, and then there will be some things that we have to do with it, like connect it to the periodic table, some periodic trends, and writing electronic configurations. This is the summary sheet that I promised for quantum numbers. So it's exactly the same stuff that I talked through in excruciating detail in the last content video. And this is what we need to know, the descriptive material we need to know about quantum numbers and atomic orbitals. So there's, the quantum number itself, what's the name of it, what's the symbol, what values are allowed, and then what's the physical significance. So we went through each of these in turn. And then off to the right here, I just included the shell model. And when we get to electron configurations and some problems where we have to decide, if we're in this shell or if we're at this principal quantum number, what values can we have and what do those orbitals look like? I think this shell model will help us remember that a little bit better and kind of the pattern with it. All right, so make sure you're familiar with this. I know that it's abstract and it's harder to memorize things that aren't connected to something for us. So it does make it a little bit tougher. I understand that. But make sure that you're familiar with the name of the quantum number. Well, I already said this, the symbol, what values are allowed. And there's homework problems where you have to go through and say, well, if it's this, is this a legal address for an electron? In other words, is this set of 4 quantum numbers permissible? Is it a real thing? And so you have to know what values are allowed for that. All right, so that's the summary sheet. And now we're coming full circle to the start of the chapter. So at the start of the chapter, I had, maybe I'll do this on the back, we had the very simple energy level diagram where we had 2 orbitals now we can talk about, and we had an electron, and we talked about popping that up into the higher orbital by adding some heat. Then the electron's up there, and then it pops back down. We can see the light from that, and that wavelength then, that change in energy was equal to, has to equal exactly the energy of the photon, Planck's constant times the frequency. So this is the simplified version. This is what we started with when I did the demo of the different metals. And so we just have these 2 states. Now that we've gone through all the stuff, right? The Bohr model, this would be more akin to this Bohr model, and then the quantum numbers and the electronic orbitals. This is what a real energy level diagram looks like. See if I can get that focused in nice for you. Of course, you have the handout, and this is off of another site, so not out of your book, but I wanted to show you the real one. So this is actually for sodium. So this is sodium, and you can see then the designation here, and when we do the orbitals for sodium, you'll see that the 3s orbital is the highest occupied orbital in what we call the ground state. And so the ground state is that lower energy, well, it's not the excited state. So when we kind of have to do electronic configurations to explain this, but it's this electron that's sitting in there is the electron on the outside of the atom. Let's put it that way for you. And so this 3s electron is the one that sodium would lose if it were going to make a sodium ion, for instance. So it's that highest energy orbital that has an electron in it when it's not excited. It's in the ground state. So back to here, we talked about this before. This would be the ground state. This is the excited state. It's been excited by adding heat to it. All right, so this really is the sodium energy level diagram. And so you can see, and don't worry about electron energy and electron volts and conversions and that kind of stuff. That's, you know, we can figure that out. But, and, you know, you would obviously be given the conversion factor if we had to. But so an electron can go into and transition to any of these orbitals, right? And so this 3p orbital, that would be the first excited state for sodium. And we want to know then, what is that change in energy for that transition? So we heat the sodium up, electron pops up to the excited state, then it comes back down and it gives off a photon, and that photon has that energy, h nu, or if we're interested in the wavelength, h times c over lambda, where c is the speed of light. You remember that, right? Okay, so we could do this calculation, in fact, because you can look at it and go over here and say, well, this energy is about -3, about -5. So does that look to you like, you know, about 2 electron volts? So about 2 electron volts. And I actually did look up the conversion factor. So the conversion factor for that is 1.6 times 10 to the minus 19 joules per electron volt. Electron volt, and don't worry about the definition of electron volts. It's all physics, right? And so if we convert that, that means that change in energy would be what? It'd be twice that, wouldn't it? So it'd be 3.2 times 10 to the minus 19th joules. That makes sense, doesn't it? So if you then go ahead and plug that in over here, we can solve for wavelength. And I suggest you go ahead and do that. But what you're going to do is you're going to find out that it should be about the 621 nanometers, which is the color of light that we saw from sodium. So that's, and you know, obviously we don't have to memorize the spectrum or anything like that, but that's getting on the longer end. So the reddish end of the visible light. So visible light goes from about 400 to about 750. The short wavelengths are blue and higher energy, and the longer wavelengths are red. So this would be kind of a reddish orange, which is what we saw. So that's pretty cool, right? So you can look at those different colors, and we could figure out from the color of the one we saw for boron or potassium, we can figure out where it matches up and what that energy level is. All right, so that's that. And that really, that comes full circle from where we started. And now what we need to do is take these, and again, you've got the handout, take these orbitals from quantum calculations, so the quantum numbers and everything like that, and just be kind of familiar with them. What do they look like? If you do, you know, not us, but if somebody does these calculations, and you know, this will show up a lot better on your screen than it does on here on the handout. They do those calculations. What does it look like? What do those orbitals look like? And we'll need to be familiar with, we need to be able to identify them from a picture, what they look like. Okay, so this site used to be my favorite site on the internet. I mean, obviously I spend more time on YouTube listening to old music, but or magic tricks. But anyway, this guy, this was so cool. This guy started this site at the very beginning of the internet, when, you know, before there were companies on the internet, believe it or not. Um, and people were putting all kinds of really cool stuff up there. He's just a chemistry professor over in the UK, and calculated all this stuff, you know, like physical chemists would do. And it's really cool. Now, here's the problem. As of last year, this site doesn't work very well anymore. It worked for, you know, what, 20 years or more. about 25, I think, is when I started looking at it. And it was such an awesome site, but it requires, uh, now I can't even remember what it requires. Flash. I think it's Macromedia Flash. And that's been, kind of eliminated. So you can still get it, it's just not supported. And anyway, so if you happen to have it on your computer because of whatever games you play or whatever, this site will still work. Uh, but as of last year, it kind of stopped working on the computers in the classrooms. Of course, I can get it. You can still get it to run if you're willing to install things that it might not be that great for your computer sometimes. Anyway, so no recommendations here on whether you install it or not, but it was a really fun site to play with because you could have it show you the different, and these don't show up very well, but the different orbitals, and you could see the equations. You could spin it around and kind of look at it from all angles. You could see a kind of time lapse photograph of it, the little dots. So it's pretty nice pictures and graphs, and it's awesome. But again, not all good things last forever, right? The only thing, so I don't expect you to learn anything from this site. If you can go in and play around with it, it's pretty cool. But if you can't, that's fine. What I want to do is just, we're not going to do anything with these equations. I just want you to understand that the equations exist and that they go through and figure out, okay, let's come up with a wave function for this 1s orbital in hydrogen, and go through and we'll do these calculations. We'll square it to get the electron density. We'll include the volume to get radial distribution of that density. Let's make sure you can see that. And so we don't have to do anything. I just want you to understand how, that these calculations exist. They're not just made up, and that's where the stuff comes from. And just kind of get a little flavor for it. We're not going to obviously do anything with it. So now what I'm going to do, since I can't show these in class, we're not in class, and I can't even play them on the classroom computer, even if we were, I just have the figures from the book. And so all I did is paste in, and you can obviously look at them in the book or in the handout. And so what do we need to know? Well, again, the different shapes of the orbitals. So an s orbital just looks like a ball, right? And it's, not right in here in the middle, that would be the nucleus. And the electron density is just kind of around that. You can think of it like an electron cloud, and that's totally fine. It's a good analogy for it. And then these graphs show the probability of finding that electron as a function of distance from the nucleus. And it's, don't worry about this too much, right? But it just shows that as you get farther and farther away, it's less likely to find that electron. So that, when you do the 90% integral of this, that would define the edge of our orbital, right? Because we said 90, didn't we say 90% probability is how we define the orbital? I believe so. And then the radial probability, all that does is it takes into account that as you're going away from the nucleus, the volume's increasing, right? So that's why it goes like this. Does that kind of make sense to you? All right, well, don't worry about it if it doesn't. What's important is just knowing that an s orbital is a spherical. And I do wish that I could show you on a computer screen so you can spin it around so it doesn't just look like a circle, because it's a sphere, not a circle. It's hard to draw that. All right, but then when you go up to the p orbitals, your book actually has really good diagrams of these that would match the calculations on that site that's no longer. A lot of books would still have these old-fashioned figure out. This is how we used to draw it on the board, just because we're not good artists, right? And a lot of books would have them just like that. just an elongated figure 8. They're really not like that. They're a lot more squished. It looks like a yo-yo. So this is the shape of the p orbitals, and you've got your, on the x-axis, the y-axis, and the z-axis. And then so you can think of these, it's hard to picture, but putting them all at the same origin, right? And see what the x, y, z p orbitals look like. So in the p subshell, there are 3 different orbitals. And you remember why that is, right? So if you had, what were the quantum numbers again? N equals 2, that's what this is. And when n equals 2, L can equal 0 or 1. The 0 is an S, the 1 is a P, right? So this is, these orbitals are for n equals 2, L equals 1, which is a 2p orbital. And there's 3 of them because when we got to the next quantum number, m sub L can be from minus L to plus L, right? So it can be minus 1, 0, or plus 1. And that's why we have the px, py, and pz. But what you're going to do is you're just going to remember that there's 3 orbitals in the p subshell, and that it's a pattern, right? And we do electron configurations and look at the periodic table, the pattern will make more sense, but the pattern comes out of the rules, right? But the pattern can help us remember the rules and the quantum numbers. All right, so enough of that. And then d orbitals, so just remember d orbitals don't look like s or p orbitals. They can look quite a bit different. And there's actually different renditions of these depending on how they define things and calculate them. And so we don't want to get into that. I'm not going to give you anything beyond d, so you don't have to know the difference between what f look, f will look even more funky than these. And so you don't have to distinguish between d orbitals and f orbitals. So obviously, if you know what s orbitals look like and p orbitals look like, you'll be able to identify d orbitals that they look, these ones kind of all look roughly the same. And then you got this cool one with the hula hoop on it or whatever, flotation device. Anyway, so that's what the orbitals look like, and that's it for orbitals. The next topic is electronic configurations, where we're going to write these out and then we're going to connect it to the periodic table. And we're finally then getting chapter 7, all this stuff hopefully tied together for you. All right, thanks everyone.